Remember, we have talked about two of the three types of heat transfer. We talked about conduction by direct contact. We talked about convection, where the material picks it up and delivers it to one thing. With both of those, did it require something to carry the energy? Yes. Conduction, the material passes it on from atom to atom, molecule to molecule. Convection, the material moves itself. But with radiation, our third type, radiation, radiant energy, light. Needs nothing, no medium, nothing required. In fact, light doesn't travel, only travels through a vacuum. Energy is transferred by electromagnetic waves. The idea here, waves. We're transferring energy by waves now. Light, radio waves, infrared waves, which we associate with heat lamps, light waves. In fact, visible light is the predominant way that we get energy. That is the most common form of energy from the sun. It's low wavelengths, even though the sun does put out that whole electromagnetic spectrum. The part that is mostly puts off visible light, the part that we can see on that. So it needs no medium. So our example, we can do a test ball example. Oscar, if you can stand up for a second. You are the Earth. You are the Earth. Okay, you are receiving energy. You are the sun. You are going to toss energy to the Earth, and the Earth is going to catch it. But we can see, just toss it, catch it. Now notice, keep going. Just like we did before, just keep doing it. Now notice, once it leaves the sun, just like since they are projectiles, is there any need for anything else to carry that energy? No, just like a projectile goes by inertia, our energy goes by itself. Nothing is required to carry it. So this is how the energy of the sun is used. Okay, thank you, gentlemen. So radiation, it doesn't require anything to carry it on that. It doesn't require anything to carry it. So we have a little video about this, about radiation here. Everybody need more time writing this down. Okay.
The story so far. Whenever there is movement and friction between two objects, you get heat. This is because the movement of molecules and heat are really one and the same. But we know that movement is a form of energy, so it follows that heat itself must also be a form of energy. That's why heat, just like energy, is measured in joules. And now, radiation waves. If you touch something that is very hot, you'll get burnt. This is because of conduction. The heat is conducted by a sort of domino effect from molecule to molecule, or from atom to atom, along the hot object and into your fingers. That's one kind of heat transfer. But if you hold your other hand above the same hot object, you will also get burnt. This is because of convection. The hot object causes the molecules of air above it to speed up. The hot air expands and becomes less dense, and is therefore conveyed upwards. That's a second kind of heat transfer. Are these the only two ways that heat can be transferred? Then why are you sitting under that beach umbrella? Because the sun's too hot? But how can the sun transfer heat to you? You're not touching it, so there can't be any convection, can there? And since most of the space between you and the sun is just that, space, except for the thin layer of air formed by the Earth's atmosphere, there can't be any convection either, can there? Because once you get beyond our atmosphere, there's almost nothing out there to do the convecting. But the sun still feels hot. Amazing. How is that possible? Is there a third kind of heat transfer which allows heat to move through empty space? Yes, there is. And to understand it, you must first of all remember that heat is a form of energy. Now, energy can travel in various ways, but one of the chief ways in which heat energy travels is in the form of waves. Rather like the waves that a boat makes when it moves through the sea, or the waves that spread out when you drop a pebble into a pool of water, or the waves that travel along a rope if you jiggle one end of it up and down. In all these cases, what you are seeing is the effect of the movement of energy itself. By means of waves, energy can move through any distance. You can do it yourself. You can make that umbrella move without touching it. Tie one end of your rope to the umbrella, and now move your end of the rope up and down. You can actually see that your energy is traveling through the space between you and the umbrella, and then making the umbrella move. The heat energy from the sun travels like that. The sun sends out waves of heat energy in all directions. Each of them is rather like the spoke of a wheel, and this is exactly what scientists call them, only they use the Latin word for spoke, which is radius, from which they get the word radiation, the name given to this third kind of heat transfer. So it's by means of radiation waves that the sun can transfer its heat energy to you and make your molecules go faster and therefore make you hotter, even though the sun is millions of miles away. Just as by means of waves again, you can transfer your energy to the umbrella and make it move, even though you're standing several meters away from it. But it isn't just the sun that radiates heat in all directions. So does an ordinary fire, or a stove, or an electric light bulb. In fact, waves of heat energy are radiated to some extent by all sources of heat. Even you radiate a certain amount of heat in the form of waves. Come to think of it, there are waves everywhere. Oh, watch out. Here comes a big one now.
All right, so see how our third type works. Now, to be a good emitter, unless you are a energy source, like, the sun generates energy and it radiates out. A light bulb would generate energy, that's fire. But other things will also emit energy. This is basically like how the earth gets warmed and things like that. Because objects will absorb energy, then re-radiate it, re-emit it. Okay, so we have good absorbers and good emitters. And in general, good absorbers are good emitters. Kind of makes sense. In order for you to be able to emit energy, you have to first absorb energy. And what happens is objects will absorb visible light and then radiate out infrared. This is how this works. So, like visible light would hit the table, your table then re-radiated out as infrared on that. Of these two, which one is the better absorber? The black Ur or the white Ur? The black one's a better absorber. Which one's a better emitter? Black one. Well, if the white one is not a good absorber, what would it have then to radiate? Nothing. Black is a good emitter because it's a good absorber. It has to be able, you have to first be able to absorb the energy. So this is a good absorber, which makes it also a good emitter. White. Poor. You have to remember something, we're going to learn something about color later on. These are not colors. Black and white are not colors. Black is the absence of color. White is all color. All right? To be defined, color, when we talk about color in physics, color has a frequency. In other words, we could point to a certain frequency and wavelength. In fact, whenever color is required on something, like running lights, like traffic lights, generally it will be specified. I know like with ships with running lights, they will specify green of this frequency, red of this frequency, yellow of this frequency. You know, there's one thing, we don't all see color the same. Color blindness aside, everybody sees color a little differently. We do. Everybody sees it a little differently. You know, because if I hold up, you know, the cone, and we would all say this traffic cone, we would say this traffic cone is orange. But I have no idea what orange looks like to you. And I know what orange looks like to me, but I have no idea. I mean, you've learned that that's orange. But I have no idea what that actually looks like to you. You see it the same way I do, and may or may not. So to be a good emitter, you have to be a good absorber, which also means if I put some iced tea in these, which one would be the better thing to keep my iced tea cooler? The white one. Yeah, because one, it's not going to absorb any heat from the outside to warm it up. What about if I wanted to put something hot and keep it, put my hot chocolate in it? Which one would I want? Still want the white one. Because the white one, is it going to emit heat from the outside very well? No. Black one is going to emit. It's going to cool down really quick. Why coffee cups are traditionally, coffee cups are made white. White is, because a white coffee cup will generally keep things cooler or hot longer, that sort of thing. White will do that. It's good emitter. Bad absorber, bad emitter. On that. A little video to show you, talk about that.
Eureka! The story so far. One of the chief ways in which heat energy moves is in the form of waves. Sources of heat, such as the sun, or a fire, or a stove, send out these waves in all directions, as if each wave were the spoke, or to use the Latin word, the radius of a wheel. This is why this third kind of heat transfer is called radiation. And now, the radiation spectrum. In warm weather, you seem to feel hotter if you're wearing black than if you're wearing white. Is this just your imagination, or are black things really warmer than white things? What could color have to do with heat? What is color anyway? Why are tomatoes red? Or oranges orange? Or buttercups yellow? Or green peas green? Or blueberries blue? Or violets violet? Where do all these colors come from? They come from light itself. White light contains all the colors. See for yourself. Go into a dark room. Open a chink in the blinds and let a narrow beam of light in. Now hold a glass prism in the light beam. Look at the colors. Red, orange, yellow, green, blue, violet. That's what white light's made of. When it shines all these colors on a tomato, the tomato absorbs each of the colors, except red, which it reflects. That's why tomatoes look red. Oranges do the same. They absorb all the colors, except orange, which they reflect. So oranges look orange. Buttercups only reflect yellow, so they look yellow. The same thing applies to green peas, blueberries, and violets. Now, if you mix all these colors together again, you get white light once more, because white is simply a combination of all the colors. Your white suit appears white because it doesn't absorb any of the colors. It reflects them all. On the other hand, your black suit appears black because it absorbs all the colors. It doesn't reflect any of them. Black is simply the absence of any color. But what's all this got to do with black being warm and white being cool? Well, when the sun radiates waves of heat energy, these waves come in many different forms, which make up a whole band, or spectrum of energy waves, from radio waves at one end to X-rays and gamma rays at the other. Some of this heat energy is visible. These are the light waves made up of all the different colors, but these only take up a little bit of the radiation spectrum. The rest of the spectrum isn't visible at all. There is, for example, some invisible radiation just beyond or beneath the red. Since the Latin word for beneath is infra, this is called infrared radiation. Now, most of the sun's radiant heat energy comes to us in the visible and the infrared parts of the spectrum. And that's why black is warm, because it not only absorbs the heat energy of the visible colors, but in doing so, it also tends to absorb a lot of the heat energy of the invisible infrared radiation as well. Conversely, white is cool, because it not only reflects the heat energy of the visible colors, but in doing so, it also tends to reflect a lot of the heat energy of the invisible infrared radiation. So now you know that color really does have something to do with heat. It isn't just your imagination. You also know what lies at the end of the rainbow. It isn't a pot of gold. It's infrared radiation.
So, a couple of ideas. Now here, the idea of the black box. Now remember, we said white is a pore absorber. Does that mean it doesn't absorb? No, it does eventually. This is proven by the black box, because notice our black box is painted white on the inside. But when I close the lid, now is light going into the hole? Yes. Is any light coming out? No. Why it looks black. Even though it's white on the inside, we can see the little hole when it's open. What happens is the light bounces around inside until it is absorbed. You have two black boxes in your body. Anybody know where those are? Your eyes. Yeah, your eyes are a black box. Now, your eyes aren't painted white on the inside. They're painted red. They're red. You can see that when you take a picture and the flash hits you directly, what happens to your pupils? You get red eye. Remember, your pupil is just a hole. When you get red eye, what you're getting is a reflection. The light is going through your pupil. It bounces off your retina, which is full of blood vessels. Blood is red. This is oxygenated blood, so it's red. Okay? And so it reflects back. This is why, one, when you do portrait stuff, is the light coming straight from the camera. And usually it's coming from an angle to avoid that. Also, there's the little red eye where it gives you a flash before it. What it's trying to do is shrink your pupils down. So that is because your pupils are wide open on that. Things like that. Try to not have direct flash. So that's the idea of the black box. Leads us to Newton's law of cooling. Yeah, same as Newton's laws of motion and Newton's law of universal gravitation. Newton's law of cooling, we could also call this Newton's law of warming. And what he found out is that the greater the temperature difference, the greater the rate of warming or cooling on that. You can try this at home. Put hot water in your ice cube tray, put cold water in your ice cube tray. See which one freezes first. Now, which means the rate of cooling is directly proportional to the difference in temperature. The greater the difference, the greater the rate. You're going to lose energy at a greater rate on this. You lose energy at a greater rate. We have a little example for this. This applies for you who like to abuse your coffee. In other words, you put cream in it. Like my wife. See, my wife and I get in this fight about going to Starbucks because my order is easy. Coffee. I drink it black. Nothing in it. You know, her favorite order is, decaf iced coffee with 4 Splendas and an inch of breve, which is half and half. Took me a long time to learn that. Breve. I guess in the barista world, that's half and half. I do not understand how breve becomes half and half, but whatever. On that. So, but some people put cream in their coffee. Question is, when should I add my cream? I want my coffee as hot as possible. When should I add it? Anyone need more time? He actually got shamed into drinking black when I was very young by an old senior chief, petty officer. But I also discovered when you're on the bridge and you can't leave, as an officer you can't leave the bridge or anywhere else, you have to send the messenger off, which is usually someone about your age, because these brand new sailors, so they're usually at 18 or 19 down to get the coffee, and when you get black coffee, they can't mess it up. Anyone still eating? We're good? All right, so black coffee. In other words, do we put our cream in right at the beginning or put it at the end? So I'm going to start out with 2 cups of coffee. And you probably discovered in our little experiment, remember, coffee urn. That's coffee, that's all that is, coffee temperature. That's all the urn produces. It starts out at about 70 C, right? It's about what it came out of the thing, about 7 degrees Celsius. We start on that. So 1 cup, I immediately put in my cream. I immediately cream it. So now the temperature of this one is at 60 degrees. In other words, my cream caused an immediately reduction of 10 degrees. And this is what the cream does. That cold cream will lower your temperature 10 degrees. Then I wait 10 minutes. I'm talking for about 10 minutes before I get to start to drink my coffee on that. And I find after that 10 minutes, my temperature is down to 50 degrees. After that 10 minutes, so I drink my coffee, it's 50 degrees. This guy decides to keep it black. They think that I'm going to add later. Now he starts at 70 degrees, and so again, he waits that 10 minutes. Gets down here. Now notice during this one changed 10 degrees. But Newton's law of cooling 1 says if you are at greater temperature, remember the environment is about 20 degrees Celsius. That's the other temperature. So we went from 60 to 20. Here we're going from 70. Remember, this is 70 to 20. Are we going to lose 10 degrees, less than 10 degrees, or more than 10 degrees? We're going to learn, no, we're going to lose more. Greater the temperature difference, the greater the rate of cooling, right? That's what Newton's law of cooling says. So after 10 minutes, this one, maybe is it at 57 degrees. You say, well, hey, it's still more. This guy's at 50 degrees, but now what does this guy have to do? Now he has to add cream. And what do we say cream does? It lowers your temperature 10 degrees. Now we're going to lose 10 more degrees. So that now when this guy drinks his coffee, it's at 47. So if you put cream in your coffee and you want the hottest cup of coffee possible, when should you add your cream? Right when you get it. Because by lowering the temperature in the beginning, we lower the rate of cooling. So it's not going to cool off as quickly on that. Remember, the cream's going to get, boom, an immediate reduction on that. Because it has to absorb some of the energy. All right? Questions? So this is how that rate of cooling works. My advice, just don't do it. Bring it black. What? Well, again, I can put up with a lot of things, you know, over the years, food, things like that. There's one thing, I'm a coffee snob. I have, you know, it's just one of those things. It's an acquired taste. Coffee is very bitter, so it's very much acquired. But then again, I like very dark chocolate, which is very bitter. So kind of goes that way too. Greenhouse effect. The last part we're going to talk about is the greenhouse effect. We are not talking politics. We are talking science. Keep that in mind. We are talking science. First, why do we call it the greenhouse effect? Well, this is because this is how a greenhouse works. Now, you guys may not have a lot of experience with greenhouses. We live in California. We really don't need them. You see them in California more in an industrial agriculture environment. Like you go around here, Half Moon Bay. You go out to Half Moon Bay, you pass the nurseries out there, they have greenhouses for their plants. But most people, very few people, have greenhouses in their backyard. Very few. Unless you're somebody who just like raises tropical plants and things like that, you probably don't have it. Back east, though, Midwest, where it snows and things like that, a lot of people have a greenhouse in their backyard. Keep their plants alive in the winter, all that kind of thing. What is a greenhouse? Well, a greenhouse just basically you have a glass house. And what happens? Well, our atmosphere is pretty much only transparent to visible light. Pretty much. Some UVA and B gets through. There's really three types of ultraviolet. There's UVA, which is, you know, when you go to if you have a black light, and you have you make your posters glow, or if you go to someplace and they stamp your hand, they run the light over your hand and it glows. That's UVA. Low energy, about the only thing, if you stare at it with your eyes, it can harm your eyes. But pretty much that's it. UVB, which is what gives you a sunburn. That's the type of ultraviolet, though it's a little more energy. It's the type of sunlight that gives you sunburn. And those two get to our atmosphere. The other one, UVC, highest energy, is like what we have in the goggle cabinet. I have a UVC light. It's what I kill any bugs. You know, when I turn on that little timer, it turns on this ultraviolet light in there, and any little bugs or anything that might be on the goggles gets killed. It's also what they use to sterilize stuff and all that. That's UVC, very high energy. That doesn't get to the atmosphere. But that little bit of ultraviolet light that comes through hits the glass of the greenhouse and gets absorbed. Doesn't go through. UV light cannot go through glass. Cannot. This is what makes glass hot. In other words, it absorbs the energy. We'll talk more when we get the light, why that happens. But it stops it. Infrared, the little bit of infrared that gets through our atmosphere, bounces off. It's like a mirror. In other words, these windows that we can see through in visible light, if we saw an infrared light frequencies, it would look like a wall of mirrors. That's what it would look like. But visible light, those are those Roy G. Biv colors. You know, the colors of the rainbow: red, orange, yellow, blue, or red, orange, yellow, green, blue, indigo, and violet. They go through the glass. Glass is transparent. It goes through. Hits the objects inside of the greenhouse. Those objects will then re-radiate. Now, we talked about good emitters, they're good absorbers, they then emit infrared. By the way, what do we usually call an infrared lamp? If I have an infrared lamp, we call it ultraviolet lamp, we call that a black light. It's a black light. It has a little bit of purple, it's not the purple part. The purple is so we know it's on. What do we call a heat lamp? An infrared, oh, let me just say. We call an infrared lamp a heat lamp. Heat lamp. It has a little bit of red, so we know it's on. Because if it didn't have the red, could we know it's on? No, it gets very hot. Just like ultraviolet light, unless we are trying to keep people from seeing it, we put a little purple. A lot of security cameras will use an infrared light, just an infrared light with no visible part of it, or just an ultraviolet light to bathe. I've seen pictures of ultraviolet cameras. You know, the police were using an area where there are a lot of drug deals. They bathe the area in ultraviolet light, so the people who are there doing the drug deal think it's dark. For the people in the camera, it was like it was daylight. You know, on that. So, but we have infrared. Well, what happened to infrared from the sun? Could it get through the walls? Well, the same thing happens with the infrared given off. Does it get back through the walls? No, it gets trapped. And so it gets trapped inside, and eventually this whole space gets hotter and hotter. And if you have a good greenhouse, you may not even need a heater. If you have enough sunny days, you may not even need a heater for your greenhouse because it's just going to heat itself naturally on that. Same thing happens to our atmosphere. Now, short, think of this as medium, long waves. What happens in our atmosphere though? Visible light. Basically we're talking visible and ultraviolet. Visible and ultraviolet hit the Earth. The Earth then re-radiates out infrared. Well, certain gases in the atmosphere, we call those greenhouse gases. Carbon dioxide is the most common, but it's not the only one. These gases then trap that infrared radiation and don't allow all of it to escape. Now, does that mean all of it gets trapped? No. Some gets trapped, some doesn't. This is how the Earth stays warm. This is the greenhouse effect. Is the greenhouse effect a bad thing? No. Is it a good thing? Yeah, depending on look at it, but it's just a thing. This is a natural thing. Do we want a runaway greenhouse effect? No. Then we become Venus. Venus. Runaway greenhouse effect. The atmosphere crushes you, dissolves you, burns you. I mean, the surface temperature on Venus melts lead. I think the longest a space probe has lasted on the surface of Venus is like 2 hours. The ones we send to Mars last for years and years and years, right? Venus, like 2 hours. If that. Not a fun place. So, we need this. Some people, well, let's try to reduce these things. Well, Earth is kind of at the outer edge of what's called the liquid water band around the sun. In other words, there's an area where you would expect to find liquid water because we're a certain distance from the sun. We're kind of like on that outer edge. If it wasn't for the greenhouse effect, the Earth would freeze up into a snowball. Now, does the Earth heat and cool? Yes, it does. Mainly because the sun puts out more energy, and the sun goes through periods where it doesn't put out as much energy. The sun actually, like during the 90s, was a very high output time for the sun. 80s and 90s. Solar output's been going down. It can go down. There are other factors. Solar output, things like that. Climatic history. Are we at a high or low point of Earth's climatic history as far as temperature? Low. Earth has been much warmer. Usually the Earth is much warmer. We're actually at the low point of that. Now, geologically speaking, we're still coming out of an ice age. That's why the Earth's temperature, on the most part, goes up. Why sea levels go up. Sea levels have been going up for the last 10,000 years. San Francisco Bay is the Sacramento River Valley. The Sacramento River used to go through the San Francisco Bay at the bottom, like we're 300 feet. Chesapeake Bay on the East Coast, big bay that's in Virginia, Delaware. That's the Susquehanna River Valley. During the Ice Age, that's where the Susquehanna River was. With Ice Age, and it fills up with water on that. So, yes. Well, the Ice Age, basically, very large glaciers cover large territories of the Earth. Well, they don't know exactly what causes an Ice Age. Conversely, they don't know why it stops either. For some reason, the Earth cools. Now, it could be a combination of you have the sun lowers its output. Things get colder. For whatever reason, maybe greenhouse gases are absorbed. But for whatever reason, the glaciers will start to expand from the north, which also increases the Earth's reflectivity. In other words, all that ice reflects all that light, away from the Earth. So you get more and more and more. So you get glaciers growing, mostly the northern hemisphere, because most of the southern hemisphere is water. A lot more water in the southern hemisphere than the northern hemisphere. glaciers grow, blah, blah, blah. Seawater levels go down because the water is all in the glaciers. Most fresh water on the most fresh water in the earth is actually frozen in glaciers. On that, that's where most of the fresh water is. So they're frozen in glaciers. Goes in, climate changes like the Sahara Desert's nice and green and rainy and blah blah blah. In the Ice Age, things go. There's been a lot of ice ages. One we just had about 10,000 years ago was not the first or the last on that. In fact, some scientists believe we might even be what's called an interglacial period. In other words, we're still in the Ice Age, but the glaciers have receded and they'll come back. Well, it's not like tomorrow morning you're going to wake up and there's a glacier in front of your house. Things like that. Now, and even in recent history, temperature goes up, temperature goes down. Go back to the Middle Ages. Middle Ages, it was a lot warmer than it is now. That's what led to the Black Plague. Plague came from China, where it came from. We opened trade with China. Plague comes from China. Goes into Europe. Fleas, rats. Well, winters were very mild, very population explosion, very good agriculture, but the rats aren't dying in the winter because it's mild, lots of rats, means lots of fleas, lots of people get bit by fleas, fleas have bubonic plague, and half the people in Europe die. Conversely, it destroys the feudal system. This is what basically changed the governments of Europe. It's kind of hard to be the lord and lady of the manor and have people farm all your land if they're all dead. You kind of have to go out and farm it for yourself. Plus the fact there's all this land that basically no one owns, so people spread out and all that. So we have changing government. So we get into more of the 15, 16, 1700s, this age of discovery. What is a driving force of why people want to come to the New World? Well, because that age in climatic history, we call that the Little Ice Age. Really cold. Really, really cold. In Europe, well, the whole world. It was a time of... No, but it is much colder than it is now. Leads to crop failures, famine, things like that. So there's a push. We want to go somewhere else. Kind of pushes to the New World. Remember, if you read about the French Revolution, they say, well, the French Revolution, because they had all these crop failures and famines and things like that. Well, what caused them? Because they were having these extremely cold temperatures, short growing seasons, and all this, like the Little Ice Age. This is what pushes the French Revolution. Okay, so again, on that. Get in the 1800s, for the most part, we warm some, cool some, goes up and down. Kind of the beginning of the 20th century, more warmer. World War II time was time cold. A lot colder during World War. During that time period was a time of colder temperatures. The 30s was very warm. 1930s. The 7 most warm years of the 20th century were in the 1930s. 7 of the 10 warmest years in the 20th century were not in the 90s, they were in the 30s. During the Dust Bowl era, things like that. We get into the 50s kind of warms up a little bit. In the 60s, we get in the 70s, it starts to cool down again. Cools down. In the 80s, it warms up again. In the 90s, and we've been cooling off again. But overall, climatic history is much colder. Like with the dinosaurs, much warmer. Much, much warmer on that. A lot of water, a lot of swamps, stuff like that. Okay, so, like I said, we're not talking politics. A lot of politics about global warming. A lot of bad science. This is good on that, yes. Who knows? I don't know. On that. I've never read anywhere where it explained why dinosaurs were so large. There are animals, there are animals today that are much larger than dinosaurs. Whales. Whales are much larger than dinosaurs ever were. Blue whale's the largest animal that ever lived on the face of the earth. On that. So, there were no marine dinosaurs that were as big as a dinosaur, as big as a blue whale. On that. But neither, that. All right, so